Alright everyone, today I'm walking you through the voltage follower experiment using LTspice. No drama, no overthinking, just clean electronics and a clean simulation. So before setting up LTspice, before starting with the experiment, we need to set up LTspice. So for that, I'll walk you through some steps and you just need to follow them. First of all, I will provide you a link uh, of GRUN and you will get this file called LM741. This would be a zip file, need to extract it, and inside there will be a folder which will have two files. So if you go and see the properties, this file is a .asy file. You have to remember this. Then you have to go to you have to copy this file, go to your C, then go to users, then to your name, and then app data, and you will be directed into this folder. After you are directed in this folder, go to locals, then find LTspice. Then in LTspice, go to lib, then go to sys, and here you just need to paste that file in the op amp section. I am pasting that file, so I have done that already. So I'll cancel this command. Then for the other file, there will be another file. Then going to the properties. So this file is a lib file. We have to copy this file. Now go back to LTspice here, the lib folder. Go into the subfolder and paste this folder. So I have done that again. So I'll cancel this command. So after doing this, you have to restart LTspice if you have an open instance. So I'll just restart LTspice. Okay. So LTspice is basically your sandbox for electronics, a place where you can test circuits before you fry them in real life. You can draw components, fire them up, run simulations, and instantly see waveform that will otherwise need a 50,000 rupees oscilloscope. So yeah, it's your superpower for this course of electron circuits. Okay, so let's start with LTspice. So we will be learning basic commands of LTspice. Go to file, new schematic. Then in the new schematic, there are some things. Let me just ensure very important. So go to tools, then settings, then schematics, and turn on the show schematic grid point feature. And from cursor type, it might be on auto, change it to black, and you might get a perfect screen. Hope you are using the version 24 1.10. Please use this version only. Going forward, to start with the experiment, we need to place components. For placing components, click on this code, right? I have clicked here. Now press P, and in this show all, go to ADS symbols. From there, you can go to op apps, double click, and the search bar, right? 4741. So this is your op amp. Place it and then right click to cancel this command. We have placed the op amp. Now we need two voltage sources. For the voltage sources, either you can go here, and placing the component you can go here. For voltage sources, either you can go here, but I would prefer shortcuts. So press V and you will have voltage source. We need three of these. So get three voltage source, then right click. So now we have the voltage sources. Now to move components, because if you can see, I'm not able to move components, they are locked to their place. To move the components, press N. So here I'm going to move this. So I'll just arrange these in the To rotate the components, while you have pressed M and select the component to move, press Ctrl R. That will rotate the components. Okay. So here we have placed the components. In the next thing we need is ground. So for ground, you can just press G and there is your ground terminal. Now we need a label. Before explaining label, I want to wire this whole circuit amount. So for that, press W. So we have wired this up. So a voltage, let me explain you what is a voltage follower type. So a voltage follower is basically simplest circuit of op-amp configuration. You feed in the input to the non-inverting terminal, which is this terminal, the positive terminal, and you loop back the output straight back to the inverting terminal. The op-amp basically says copy that. So gain of the circuit is 1, output is equal to input. No amplification is there, just loyalty. But the magic is high input impedance, it won't load your previous stage, and low input impedance, it can drive the next stage easily. So in short, you can say it acts as a buffer, like a soldier holding the line, so that the rest of the circuit doesn't collapse. Now, the components we have used is a LM741, 2 power supplies, and 1 input source. So now I will explain you net. For net, you can press N command, and net is basically a label. Or let me just show you. Set it to output first, copy the commands here, and tell you. So basically what a net does is, let's say if I want to connect this V1 positive to V2 negative, the one way is to either run a wire like this, okay, or what else I can do is I can put a net label, bidirectional net label. So a net label basically teleports your values from this point to this point. So why are we adding an output net label here? So that because this point is left not connected to any external source. So what happens is this gets a bit of issue in ERC. ERC is electric rule check. So basically in SPICE software you get a ERC. So we don't want a ERC, so we are connecting it to our output label. So see, you can see here it's a join now and ERC won't fail. Now we are setting up the voltage supplies. For setting up the voltage supplies, just right click on the voltages. Now on the voltage sources, and you will get this dialog box with a DC value and a series resistance. Series resistance is nothing but your internal resistance, so leave it 0. And on the DC value, we will add 15. And for this, we will add minus 15. So we have got the two values, but just a second here, we will not use minus 15 as we have already used the minus terminal of the battery. Now, we need a sine wave to confirm the working of this voltage follower. But we won't see any sine wave or wave element here in LTspice. So what to do? So basically we will convert this voltage source into a sine wave source. So how to do that? Right click on this, go to advanced settings. And here you can see an option for sine wave. Go to sine wave. For this current one, I am using a DC offset of 0. And amplitude would be 5, so that it will give me a peak to peak voltage of 10 volts, which is basically a peak to peak sine wave of 10 volts, which means each half of the sine wave is a peak of 5 volts. And we will use a frequency of 100. So we have a sine wave source, 2 voltage sources. Then we have to run the simulation. For running the simulation, there are 2 steps. The first step is to configure the analysis. So we are configuring the analysis. What does it mean? In LTspice, this command means that the transient analysis can be done for how much time, and time to start the saving data. That means when you want to start logging in your data and maximum time steps. So I don't want it to go for a long time. So I'll just have this as 2, 1 and 0. So I'll want you to keep these values same. Don't change these values. You can set it anywhere. Next thing is we will use the text tool to add some descriptive text. So here I'm just writing voltage. You follow circuit using LM741 and this means. So I'll raise this here and again press T and you will be you will put your name and your enrollment number. I'll just put my name here. So these are the two steps. One is setting the transient analysis value, and second is pasting your descriptive text here. Now rules will read, so you can press Alt R or you can go here and press the run button. So you will see the oscilloscope. So now you will also see when you are taking your cursor to any wire, it is getting a symbol of red probe. So for placing the probe, we will first probe the output. So for pressing it, just left click and you are seeing the voltages here. So the voltage here is in a waveform sine wave and it's a peak to peak of 5 volts. Now, if you right click on the x axis, you can see this horizontal axis thing. So what you can do is I'm just changing it to 0.0. So it is giving me 10 millisecond waveform view. I want a 100 millisecond waveform view. So here it is. So basically now we can clearly see the peak to peak 5 volt voltages, right? Okay. But I also need to compare the input. So for comparing the input, I'll just go and add a plot above. So this is called a plot. Now I'm going to add a plot, then that add base and go to voltage number 2 because V1 is basically this. So sorry, V1 is basically your 15 volt supply and V3 is also your 15 volt supply. So I'll go with the V2. Okay, and below this is clear for the integral. We are just going with V2 and so if you can see both the waves, this blue one is your input wave. So this is also 5 volt peak to peak and your output is also 5 volt peak to peak sine wave, which is exactly what it needs to be done. So it's a voltage follower, so it's following its path. If you can see, it's exactly the same. Now we will calculate the slew rate of this op-amp. For calculating the slew rate of the op-amp, we need to change this sine wave to a square wave. So how to do that? Because again, we don't have a square wave function if you see, but we have a pulse function. So with the pulse, there are some settings that you have to remember again for everything. So I'm going with the initial value of -5 because I want a 10 volt peak to peak square wave. Then the delay of the square wave should be 0. The rising time of the square wave is 1 microsecond. Fall is also 1 microsecond. So on time you can keep it to 50 microseconds. And the period you can keep it to 100 microseconds. Cycle, the end cycle, that means how many cycles you have to uh, feed in the circuit. So here we need an infinite cycle because we are skew rate calculation. So leave this blank for sine wave also and for square wave also. Now, okay. So I'll just move this text here. So these are the settings which you have to remember for sine wave, sorry, square wave. Now again, run the simulation. For running the simulation again, you can just do not click run. So the simulation is running. Now my both the windows have been minimized. So I'll just bring back this window. Okay, so my simulation window is here. Again, I'm going to program, and I also want my input, so I'll bring the input also. So both of these values are here. Now we need to change the time slowly. So I'll set it up to 100. Let's see. That's too much. So let's set it in this. Okay, quite nice. Let's set it on 1 millisecond. Okay. So we are fitting on a square wave and we are getting the output as a sine wave, which is mixed with square wave. So basically, this wave, which is here, this helps us in the slew rate calculation. So we have successfully included that how the voltage follower circuit works. And now I would like to give you some observation. So when a follower sees a sine wave, the output transits like a shadow. So basically, we have seen same shape, same amplitude, no delay, no distortion. As long as you stay within the limits of LM741, it would be like that. But when I fed square wave, you notice the LM741 struggles a bit. The output becomes a slope instead of the perfect square wave. So you can see the outputs have become slow. This is because of slew rate limitation. The op-amp can't climb the voltage instantaneously, this voltage. And ladies and gentlemen, is the real beauty of simulation. So you see how actually components behave, not how your textbook pretends they behave. So in conclusion, a voltage follower gives you a unity gain, but massive stability. It isolates stages, protects signals, and keep your systems disciplined and clean. And LTspice lets you test all this without burning wires or blowing up components. That's the experiment, straightforward, precise, and effective. Hope that helped. LTspice looks complicated, but once you run a few circuits, it becomes your battlefield map. Thanks for watching.